Okay, so for this mission, you're going to imagine you're a sociologist and you're looking at how people view Wall Street executives. And we're looking at this data set here that looks at different variables, gender, whether they rent their home or not, their social class, and whether they view Wall Street executives as these different characterizations. So you can see the mission is separated into different categories. So the first part is on working with chi-squared, one-sided chi-squared goodness of fit test. And then the second part is working with a two-way chi-squared test for independence. And then part 3 goes over the one-way chi-squared goodness of fit test in R. So looking at the data set that we've provided. Part 4 deals with the two-way chi-squared test for independence in R. So it's pretty straightforward. So this mission will handle the one-way chi-squared goodness of fit test and the two-way chi-squared test for independence. So it's a lot of what we went over earlier in the section that we had earlier this morning. So I'm happy to go over anything if you have any questions about the material, or one of the questions and it makes sense, and I'm happy to go through it to clarify it with you. Do you have anything in particular you wanted to go over? Right, so for the first test that we went over in this module, we talked about the chi-squared one-way goodness of fit test. So this is a hypothesis test, like we've been learning in the previous modules. And for any hypothesis test, you're gonna have the same 5 steps. So you're gonna do the same thing for every single hypothesis test that you're running. And the first step is to state the null and the alternate hypotheses in terms of the null and the alternate hypothesis. And second is you're going to select a significance level alpha. And then third, you're going to compute the test statistic. So in this case, for the chi-squared test, you're going to compute the chi-squared goodness of fit test statistic. And then the fourth step is, assuming the null hypothesis is true, you will make a decision by either A, comparing the test statistic chi-squared value with the critical value, and you can make a conclusion from there. Or second is you can look at the p-value, and you can compare the p-value with your alpha significance level value. If the p-value is less than the alpha value, that's a significant result, and you will reject your null hypothesis and conclude with your alternate. If the p-value is greater than your alpha value, you will not reject your null hypothesis, and you conclude that you will fail to reject your null hypothesis. And finally, you will state your conclusion based off of that. So we went over earlier how to compute the test statistic for the chi-squared. And we also discussed how to compare with the critical value. So the way to find what the given critical value is you can use R in order to find the critical value, which you'll be using for comparison with your test statistic to conclude with your test. Or you could also use a chi-squared table that has values in it, which is the older method that we don't really teach you because using R is a more easier and exact method. So to figure out your conclusion, what you'll do is you'll compare your test statistic with your critical value. So once you found what your critical value is with your given degree of freedom, because we can see here that the chi-square distribution will adjust, it will change based on how many degrees of freedom you are working with. And remember, the chi-squared goodness of fit test has a different degrees of freedom calculation than the two-way chi-square test for independence. So for the one-way test, goodness of fit test, you will calculate degrees of freedom by taking k minus 1, where k is equal to the number of categories. And remember, for the two-way chi-squared test for independence, you'll be taking the amount of rows, subtracting 1, and you multiply that by the number of columns, subtracted by 1. So just be aware that depending on which test you're running, you will have a different degrees of freedom calculation, and thus you'll have a different critical value associated with that depending on the test that you're running within the chi-square distribution. So in order to make a conclusion is you will find your test statistic by using the formula for chi-squared, which we said is the observed minus the expected, or sorry, the expected minus the observed squared divided by the expected value, and then you will sum that for each category. And the summation of that will be equal to your chi-squared test statistic. So once you have your chi-squared test statistic, you can then compare it with the chi-squared critical value for your given distribution. And if the test statistic is more extreme than the critical value, you would reject the null hypothesis and you'll conclude with the alternate hypothesis. And then alternatively, you can also look at the p-value. So if your p-value from your hypothesis test is less than your alpha value, you will reject the null hypothesis. If your p-value is greater than your alpha value, you will not reject the null hypothesis. So that's what we were talking to earlier about when to reject and not reject the null hypothesis for your conclusion. So you have two methods. You could either compare the test statistic with the critical value, or you could compare the p-value with the alpha value. And from that information, you'll come up with your conclusion. Right, so the question was regarding two-way tests and one-way tests and looking at the significant regions of rejection. So as you can see here, for a normal distribution with the 0.05 alpha, you will have the two critical values on either side of positive 1.96 and negative 1.96 on the left side. So that means that, as you can see in this diagram, the critical any test statistic that falls in between those two critical values in the region colored green, you will not reject the null hypothesis. However, if you have a test statistic that falls more extreme than the two critical values, that is to say, if it's greater than positive 1.96 or less than negative 1.96, if it falls in either of those two tails, colored blue or brown in this diagram, you will reject your null hypothesis because that's a significant result. And this is for a two-way test, right? And then the question was about a one-sided test. So we can look at a right-sided test. So if you're dealing with a right-sided test, that means that, as we said in the last example, we had a 0.05 alpha. So that was a two-sided test, which means that on each of the two tails, there was 2.5% alpha on each of those two tails that encompassed, in summation, a 0.05 alpha. But in this case, because we're only dealing with a one-sided test, that 0.05 alpha region is all going to be on one tail. So in this case, with a right-handed test, we have that 0.05 alpha region on the right hand without the left side, so it's a greater region, as you can see here. So that means that instead of having two critical values, you only have one critical value, and because that's dealing with the same amount of that alpha value, that significance level, it's going to be a greater tail. So remember, in the last example, on the positive end, we had a z critical value of 1.96. In this case, because it's a one-sided test, the z critical value is 1.645. So you can see it's a larger tail. So in this case, if you're going to compare the test statistic with the critical value, you're going to use the critical value of 1.645. And if you have a test statistic that's greater than 1.645, you'll reject your null hypothesis if it falls in that tail, which is colored blue. But if you have a test statistic that falls in the green region, in that 95, 95th percentile, you will not reject the null hypothesis in the region that's shaded green. So that's with a right-handed test. And then when you're dealing with a left-handed test, it's the same thing going in reverse on the left side. So now you only have one critical value here, which in this case is negative 1.645. So in this case, what you're looking at is whether the test statistic is less than negative 1.645 or greater than negative 1.645. If it's less than negative 1.645, that's a significant result and you reject your null hypothesis. So if the test statistic falls in that tail with the green shaded region, that would be a significant result. If it lands within that blue shaded region, that is not a significant result and you do not reject your null hypothesis in that case. Does that make sense, Fatima? Okay, great.
Hello, Justin. Can you hear me?
Hi, I can hear you.
Hey, this is Diego. For some reason, I can't type on the chat, but I have one question about the mission 8, the mission from last week, I believe. I was going through that mission again, and I was trying to get the right answers and the ones that I got wrong.
Mm-hmm.
And I have the last two for some reason. I'm not sure what I'm doing wrong, but I can't get the right correct answer. And question 29 and question 30.
Sure. Yeah, we could take a look at that together. I'm just pulling it up now. So you said mission 8.
Mm-hmm.
And which questions are we looking at? The last two you said?
The last two, yes.
29, 30?
Mm-hmm.
Okay. So this is looking at the science data set
mm-hmm.
and the accompanying R code. So I'm going to pull up RStudio. We're going to load in the science data set and the accompanying R code. So let me just load that in. Okay. And let's take a look at the last two questions. So question 29 says, using your results from question 28, what do you conclude at alpha of 0.10? Well, let's look at question 28 then. Question 28 says, using statistical software, conduct a two-sided test of the hypothesis that there is no difference between the proportion of men and women who view biology as scientific. What are your hypotheses in terms of H naught and H alpha? So what did we say the answer to this question was?
That was H. So the null was P female minus P male equals 0. I believe it's the second option you have there.
So it's this one then, right?
Yep, that's the right one.
Okay. So first we stated our null hypothesis and our outlier hypothesis, and then question 29 is asking us to come up with the result of that test. So in this case, now we can actually run the test in R. So I'll pull up RStudio and we can take a look at this together.
Mm-hmm. Oh, okay, sorry. The 29 is actually, I mean, I did get it. It's just the question 30 that I didn't get. Because the p-value is, I can see 0.49, so 0.5, and we're looking at the alpha at the level of 0.1 was greater than that. So we failed to reject the null here. But then in the question 30, that's the one that I'm not sure how you get that number. What is the point estimate? I didn't know how to get that number, the point estimate.
Yeah, sure. So we could go over it. So so first I ran the test. So this is a portion test looking at biology, and it gave it a p-value of 0.4957. Right, and then so that's how we would do question 29. And question 30 is asking, a famous sociologist approaches you and wants to know if the average age differs amongst people who view sociology as scientific or not. She thinks that older people might view sociology as less scientific than younger people, since the nature of sociological studies has changed over time. Using statistical software, conduct a two-sided test of the hypothesis that there is no difference in the average age amongst those who view sociology as scientific versus those who do not. It says, what is the point estimate? Round your answer to 2 decimal places. So we can run the code. This is a t-test looking at age and sociology. So we're going to see if between the ages, if there is a difference in the mean number between those two groups in the sociology variable. So we're gonna run this t-test, and we see here that the results of our 2-sample t-test, we have a t-test statistic of -4.97 with 1645 degrees of freedom, and our p-value is 7.4 times 10 to the -7, right? So this is a significant result, right? And it gives us some sample estimates. So the sample estimates, the point estimates for the mean in the scientific group is 44.7, and the mean in the non-scientific group is 48.63. And the 95% confidence interval we can see here is between -5.46 to -2.37 for the t-score.
Sorry, was that a question, Justin?
No, I'm just actually rereading the question. I'm just going through it. So, okay. So let's look at the question again. So the question here, there you go.
Yes.
we can go through the question again, and then we can look at our results. So can you see the question? Is it coming up?
Yep, I can see
great.
it.
Okay, so it's saying we're looking at the average age amongst these two groups, and we want to know if there's a difference in the age between those two groups or not, right? So we're running a t-test to see whether there's a difference or if there's no difference in the average age amongst these two groups, and it's asking what our point estimate is, right? So in order to do this test, we'll be running a t-test, but the best way to do that would be is you can actually take the average ages of the two groups, and you can structure your hypothesis test to say that the average age in the one group, the one who views sociology as scientific, and those who do not, you can actually subtract the means of those two groups, and your null hypothesis will be that mean is equal to 0, and the alternate hypothesis would be that mean is not equal to 0. So that's how you can structure your hypotheses for your hypothesis test, and then we can run that test within R. So just going back to our analysis in R. So what we can see here is we see that it's a significant result because we have a very significant p-value. It's a very, very small p-value. So we can conclude that they are not the same ages. And here we see that the sample estimates for the two groups, for the two means, is the mean in the group that is not scientific is 48.63, and the mean in the group that's scientific is 44.72, right? So if we go back to Viola's hypothesis, where we said the null hypothesis would be the mean age in the group of scientific subtracting out the mean in the group that's non-scientific will be equal to 0, and the alternate hypothesis would be that it's not equal to 0, then we can then come up with our point estimate for this test, right? Given the information we have here. So what we can do is if we subtract, if we take 44.72 and subtract 48.63, we should come up with our point estimate. So we can do that here. And we got negative 3.9162.
Okay.
That's the answer that I came up with.
Okay, perfect. Got it now. Thank you.
Sure. And does that make sense?
Yep, it does make sense now. Sounds so much easier when you say it, though.
Great. Glad that helped clarify. Did you guys have any more questions? Okay. So it looks like Fatima doesn't have any more questions. Diego, do you have any more questions on your end?
I'm good for now. I'm actually starting to write the test. I'm describing the data right now, and I've been asking a couple of questions. I think I'm good to go with everything that you guys provided.
Okay, great. Well, just reach out if you guys have any more questions, and good luck with the mission, and with working on your final project as well. And reach out if you guys have any other questions. Happy to help.
Perfect. Thank you.